Welcome back to ECE 441A, 541A. The next time you come to this class officially, hopefully you will make Friday your official next time to be here. The next time this class is scheduled to play out is Friday morning. That's the date of our exam, the first exam. Homework 2 is due today, and you can turn that in now, later to my mailbox, or later to the Dropbox in D2L. I would encourage you to look at the practice exams on D2L to get comfortable with the style of the exam and the types of problems. Lab number 1, you should at least know what's going on in lab number 1. You do not have to execute lab number 1 prior to exam number 1, but I think it will definitely help you in exam number 1 if you know what's going on in lab number 1. In terms of office hours, today I have the normal office hours from 9 until 11. There's also the normal office hours on Thursdays from 11 until noon, and somebody asked if I could have some additional office hours, so I think these are available in terms of time slots. The 4 o'clock may not work if you're in the capstone, so that's why I've given you another hour from noon to 1 tomorrow. That's what's happening in the next couple of days prior to the exam, which happens on Friday. Today, what I want to cover is the process for exam number 1 and finish up deriving the relationships for an underdamped second-order system to do the identification. That's what I mean by the ID. That's system identification for a second-order system. The process for exam number 1, you will be allowed 1 sheet of notes, front and back. You can bring in a copy of the Laplace transform table. Is that in the exam 1 material? I believe it is on D2L if you don't have the textbook, but you can bring that. You'll then have 2 pieces of paper in front of you. You can have a calculator and something to write with, but that's it. And yourself. You need to come here ready to go for exam number 1. Are there questions about the process? Good. It's clear. Let's then pick back up with our second-order system identification problem, and maybe as a little bit of a review, you can actually hopefully connect what we're doing with this mass spring damper system. This is what you're doing in the lab. You have a mass spring damper system with a mass, a spring, and a dashpot, and some applied force. You should be, by Friday, if you aren't already, very comfortable with deriving that equation that governs the dynamic behavior of that system. That's mx double dot plus, or x double prime plus bx prime plus kx is equal to gamma u. You can now Laplace transform that equation. You're wanting a transfer function. You can neglect the initial conditions. You're just wanting the transfer function. You now have an s squared m plus sb plus k, all multiplying the Laplace transform of your position variable, and the input then is on the right, scaled or weighted by a gamma u of s. You can divide that out, and you now have your transfer function. If you want a monic polynomial in your denominator, do you remember what monic means? Mono, 1. Your leading coefficient is 1. We've scaled the denominator to produce the leading coefficient in your denominator equaling to 1, and sometimes that's easier or cleaner. That now explicitly identifies the 2 unknown variables in your denominator, and you have that unknown constant coefficient in your numerator. you can then hopefully see the connection with the mass spring damper expression as a transfer function and this generic second order transfer function that we've been playing with in the last few days in this class. And we can write this transfer function many different ways, or the denominator, it has several different familiar forms or variables that you might be parameterizing that denominator with respect to. You have the sigma, which corresponds to what? The sigma corresponds to the real part of your root, doesn't it? That's the horizontal, and it's actually because we have s plus sigma, we are now into the left half plane, a distance minus sigma. The omega sub d is our damped oscillation frequency, and the alpha is just a numerator constant. And we could rewrite that a different way in terms of our damping ratio, zeta, and our omega sub n, which is the natural frequency, which I'm hoping that you can, if you don't sketch it, you at least mentally have this picture in your mind of what's happening in the S-plane with respect to the two poles. And I'm just looking at the top half of the complex S-plane. It's a mirror image below because everything appears in complex conjugate pairs. This now illustrates where we are in terms of location of our pole in this underdamped second order system. We have a real part of minus sigma, an imaginary part or a vertical distance away from the real axis as omega sub d. We can start then relating these pieces to the other expression or parameterization of the denominator. Omega sub n, our natural frequency, that's the distance we are away from the origin in the S-plane for that pole. And we can find that from the Pythagorean theorem. We can say, well, we know that a squared plus b squared is equal to c squared. And this is going to actually allow us to rewrite or re-express the damped frequency in terms of our damping sigma and our natural frequency omega sub n. We also know that this distance sigma can be written as zeta omega sub n. If we do that, then we can say that up here we can solve that for omega sub d squared. And if we replace sigma with its parameterized form in terms of the natural frequency, sigma is the natural frequency times the damping ratio zeta. We square that up, or do the squaring operation, and factor out the common term. If we now take the square root of both sides, we see a relationship that we might use that relates the natural frequency omega sub n to the damped frequency omega sub d, and it's related by this damping ratio zeta. So you might see in some of the subsequent discussion the use of this expression. Omega sub d is equal to omega sub n square root of 1 minus zeta squared, and that's just coming from the way we've parameterized that pole in the complex S-plane. There's nothing really magic here, it's just the Pythagorean theorem. So if that looks weird, just go, wait a minute, this is just a squared plus b squared is equal to c squared. This is fine, I know what's going on here. The other thing that we can do is sometimes we might be interested in discussing or talking about that angle. The bigger that angle, the less damping we really have. And that really says that we have more imaginary part than we have real part. That angle gets above 45 degrees, then we're going to have more oscillatory behavior. We have less damping relative to the oscillating part of our response. Now we simply go back to our trig and we say the cosine of that angle is the real part over, the adjacent in trigonometric terms, the adjacent over hypotenuse, but the adjacent we can rewrite in another parameterized form as zeta omega sub n, and there's where that zeta comes from. Now, later we may, in our derivation, talk about the sine of theta. We mainly focus on zeta, which is the cosine of theta, but in today's development, we might want to refer to the sine of that angle theta. That's now opposite over hypotenuse, or omega sub d over omega sub n. Now let's go ahead and use that relationship that we had just derived for omega sub d, omega sub n, and zeta. And now we see that the sine of theta can be written as the square root of 1 minus zeta squared, and I might just call that beta, just because I get tired of writing the square root of 1 minus zeta squared. Questions on that? Now you have this picture with all of these parameterizations for locating that pole, or one of the poles of our complex pair of poles in the complex S-plane. And we know the further we are in the real direction into the left half plane, that corresponds to more damping. Our exponential damping rate is enhanced. The further we are away from the horizontal real line in the vertical direction, that gives us more oscillation, so our bumps are closer together in our transient response properties. Let's now use that information to move forward with relating the time domain step response to these locations in the S-plane. In the step response, that's the picture in our block diagram form. And G of S, we could explode that in many different ways for the exam. I might say find G of S, and G of S might actually be a very complicated interconnected block diagram, and you'll have to find that G of S, for example. I could really theoretically give you one problem on Friday's exam, and you would have to solve it, right? All right, we won't go further, but you know my joke on that one. I just make it so difficult to start that you can't start. I have to just grade the first piece, and then I don't have to grade the rest of the exam, because you've missed the first piece of that long derivation. That's why I probably won't do that. I'll just have it separated into pieces and parts, but you now need to be conceptualizing this as a whole. All of this stuff is interconnected and interrelated. You can find a system, G of S, and then you can start analyzing what's going on with that system. For our purposes, let's let the input just be a constant of amplitude A. That's what we will then use for the Laplace transform of that step. If it was the unit step, capital A would be 1. But using A of S, we can now say that Y of it, or using R of S, we can now say Y of S is our second order transfer function times A over S, or we could multiply that out. Or we could write it in terms of the natural frequency and the damping ratio zeta. All of those parameterizations are possible. And that shouldn't set off any alarms, those parameterizations. Yes? Am I missing a power of S? Thank you very much. I am missing the power of S, aren't I? I forgot that I had applied a step to that. So let's do this. Is that better? Thank you for waking me up. That alarm, that's why the alarm went off, is to warn me that that particular S was missing. You may not have such an alarm on the exam. You'll just have to do that in your own head. Alarm bells will be ringing, and you'll go, oh, I missed that, and you'll be able to get that on the exam. Where were we? Let's now rewrite that a little bit differently to make our analysis maybe a little cleaner. Let's now take this A alpha upstairs, S times S squared plus 2 zeta omega sub n S plus omega sub n squared, and let's now multiply that by 1. The reason we are doing that will become a little more clear as we move through the derivation, but for now what I'm wanting to end up with is a numerator that just has omega sub n squared in it and a denominator that just has that first piece to it, which says that I really, right now, I'm not too concerned with this scaling factor. That's just a number. We've hit it with an A for amplitude. Alpha was a constant, and omega sub n, our natural frequency, is a constant. What I'm more interested in is this expression, omega sub n squared S times the quantity S squared plus 2 zeta omega sub n S plus omega sub n squared. And I will probably refer to this unscaled part of our expression for capital Y of S as capital Y bar of S. What we want to do now in this second order system identification process is to actually find these parameters, let's say omega sub n, zeta, and alpha, from the time domain step response. What we will identify or pull from the step response will be our peak time, time to peak. We will find the percent overshoot, and we will also find the final value. Those three values from our time domain step response will allow us to back out the natural frequency, the damping ratio. Those could be used to find the damped frequency, and then we will find the gain in our system, alpha. The pictures that we have for this parameterized form of capital Y of S, just to provide an image for what we're doing with the step response. Here's time, and let's say that those are supposed to be scaled versions of the other. They may not be quite properly aligned, but the peaks are supposed to be lined up, and all the bumps and dips are supposed to be lined up. The red curve is supposed to be our full response, and the blue curve is the unscaled response. The blue curve is just this inverse Laplace transform of y bar of s. And what we can identify from this picture are several things. Here is our peak time. That's the same for all of these. We can identify this will eventually go to a final value. We can call that y sub bar of final value. And we will actually show, or you can see, that that's equal to 1 if you apply the final value theorem to that capital Y bar expression. And then this will also go to some final value, y sub final value. And in the notes to the lab, I may call that capital A sub 1. This point here is the maximum value of our full response at the time when we peak, and this value is y bar at the time that we peak. We now want to find a way to relate this peak, the final value, the time to peak, all of this to, or to find omega sub n, zeta, and alpha. If you wanted to find when y bar of t sub p reached its maximum, what would you be thinking about in terms of calculus? You would want to know, when is the derivative of y bar equal to 0? That will allow me to figure out what t sub p is. That would be the time when that happened. I could plug that time back in and evaluate to find y bar of t sub p. So I want to do some calculus, but we're going to do it a little differently. We're going to do it in the frequency domain. We want to differentiate little y sub bar of t in the frequency domain. What does that correspond to? Multiplication by s, doesn't it? And we have our expression for y bar. So if we're looking to try to find when that peaks in the time domain, what we're wanting to do is we want to now find the relationship between the time to peak and omega sub d. If somebody gives you the time domain response, you can go find that maximum and find the time that that occurs. So you can measure time to peak, t sub p. You want to now translate that into an omega sub d so that you know the vertical distance your pole is from the horizontal axis in the s-plane. And that will get you partway towards identifying your plant, capital G of s. If we look to try to find this relationship, we said, well, let's differentiate little y bar of t in the frequency domain. That's like multiplying by s, capital Y bar. We have an s, and then we had our expression for y bar. Now, if we look at this, that s cancels that s, and oh, that's almost in the form that we want it to be in. That's almost a clean Laplace transform pair. If the numerator was simply omega sub d, no squaring, if it was just omega sub d, we would have what expression in the time domain? We now want, if we could find this, or if we had this, which we almost do in the blue, how do we get that? Can I not scale this that way and I have what I had just above in blue? Did I do the algebra correctly? I didn't do black and blue, I did black and red, so you're not quite black and blue over this derivation, but you can hopefully see that in the red is what we want, and all we're really doing is scaling that if we now inverse Laplace transform. This we can easily, I'm claiming, inverse Laplace transform. That's a damped sinusoid. All we're doing is scaling that by some number, the natural frequency squared over omega sub d. Meaning, if somebody says, oh, d by dt of y bar of t is just the inverse Laplace transform of s y bar of s, but I hope you can see from that red boxed expression that's now just omega sub n squared over omega sub d times what I've highlighted in yellow, which is e to the minus sigma t sine omega sub dt. Or y prime bar of t is now omega sub n squared over omega sub d, e to the minus sigma t sine omega sub dt. Why am I doing this? Remind us. We did all of that to try to find the relationship between the peak time in this step response curve. And you said from calculus, if we set that derivative equal to 0, then we'll be able to evaluate for when that happens, when that peak time occurs. Here is our expression now for the derivative. We've now derived an expression for the derivative. We want to set that equal to 0. Well, e to the minus sigma t, that's always non-zero unless it's way out in infinity. So let's not worry about that piece. Omega sub n squared over omega sub d is constant. Sine omega sub dt, that has a lot of times that it's equal to 0, doesn't it? We want to know when is the first time after t equals 0 that this guy hits 0, and that's where we want to find that maximum in our y sub bar of t expression. We want to look then, this is the key piece, when we are setting y bar prime of t equal to 0, we want to know when is the first time that happens after t equals 0. Or we're now saying find a non-zero value of t, the first or the smallest non-zero value of t that causes sine omega sub dt to equal 0. What do we know about the argument of the sine if it's supposed to equal 0? If it's non-zero, pi, or some multiple of pi, and the first one will be pi. That means that we need, for this to happen, we need omega sub dt to equal pi. And when is that going to occur? The first time at the peak time, T sub P. So this now says T sub P is pi over omega sub D. This is our peak time. And that's one of our relationships. If you physically go to your time response and you measure the peak time, let's say that occurs at a half of a second, now you know what omega sub D is, because you know pi, that's a constant. Now you just solve this for omega sub D, and you have your damped oscillation frequency by simply measuring the time it takes you to reach your first peak. So you could write it either this way, T sub P is pi over omega sub D, or you can say T sub P can provide omega sub D by just solving for omega sub D. And that's the same expression, just reorganized. You need the damped frequency. You have it if you measure your peak time, if this is a second order system response under damped. That's the first relationship. The second relationship is we want to now find the relation. Yes, question? Yes, so this, what we're trying to do is we're trying to take our time domain. So the question was, is this a relationship between frequency and time domains? We have available to us, we've kicked our system, we've hit it with a step, it now goes and shakes. We can measure those time instances, and we can now identify that from that time response plot, we know when it peaks the first time. We use that peak time now to inform where is our pole located in the complex S-plane in terms of its vertical location. We now know omega sub D. Is that clear? We now need to know where are we over into the left half plane. We know the height we are above the real line. Now we need to locate it more accurately by figuring out how far into the left half plane is it. What is our sigma? We're going to do that by finding or relating the percent overshoot, which we can find from our plot. We can compute the percent overshoot from our time domain plot, and we're going to relate that to our damping ratio zeta. So let's now find the percent overshoot which I will subsequently just call PO, and damping ratio, which is zeta. We want to find that relationship. What's zeta give us? When you hear zeta, think angle, because zeta and the angle theta are connected. Cosine of theta is zeta. We now know where we are vertically. If somebody gives us the angle theta, we know exactly where we're at, horizontally and vertically. So if we can find zeta in terms of or from the percent overshoot, we've located that pole location. The only thing that hasn't been done is finding the gain. And we'll have to use a different relationship for that. But here, if we look at what we have, do you remember how to find percent overshoot from a piece of data? And you can do this for y bar or y. You don't have to know y bar. We're doing y bar to help us with the derivation, but in reality, you're going to have y of t. You can find the same percent overshoot in y of t. It's going to be exactly the same as it is in y bar of t. For us, we know that this occurs at t sub p. This value is y bar of t sub p, and eventually this is going to go to some y bar of final value. And we're actually going to show that that's equal to 1, and this we might call just y sub bar peak. Where does y bar peak? What time? Time t sub peak. That's pretty easy, right? So the peak, the first peak of y bar of t occurs at time t equal to t sub p. And we actually have an expression for y bar of t. T sub p is pi over omega sub d, but our y bar expression, that was 1 minus, well, maybe I haven't derived it, but I derive it in the notes to demo number 1. So if you want to see where this is coming from, go back to note 1 in demo 1, page 8 of your demo 1 notes, and you'll find this derivation. It's 1 minus 1 over beta. Beta was just the square root of 1 minus zeta squared, times e to the minus sigma t sine omega sub dt plus theta. There's a lot of familiar parameters in that expression for y bar of t. So let me just say see note 1 in demo 1 notes. And in this expression, beta is 1 minus zeta squared, and theta is the inverse cosine of zeta. We want to now evaluate that at a particular value of time, which is t sub p. If we do that, y bar at t sub p becomes 1 minus 1 over beta e to the minus sigma. T sub p is pi over omega sub d. Then we have sine of omega sub d pi over omega sub d plus theta. And let's look at this in two different parts. We have part number 1 and part number 2, and we can sort of separate those out and evaluate those separately. What's happening for these two different pieces? Piece number 1, we have e to the minus sigma pi over omega sub d, where this was just the peak time. But this is e to the minus sigma is zeta omega sub n, parameterized in that form, and omega sub d is omega sub n square root of 1 minus zeta squared. Those omega sub n's cancel, and we now have that this piece is equal to e to the minus zeta pi over the square root of 1 minus zeta squared. That's our first piece. What about our second piece? If we go back here, the omega sub d's cancel, and we have the sine of two angles, pi and theta. We have to go back to our trig. We have the sine of pi plus theta. That's just the sine of pi cosine of theta plus cosine of pi sine of theta. What's the sine of pi? 0. So that first term vanishes. What's the cosine of pi? That's minus 1. This now becomes minus sine of theta, but sine of theta we just were calling beta. So the sine of pi plus theta is just minus beta, and we can now evaluate y bar of t sub p. It's now 1 minus 1 over beta, the first piece, e to the minus zeta pi over the square root of 1 minus zeta squared, sine of theta, or pi plus theta, which was now minus beta. Boy, things start cleaning up, don't they? This positive cancels, that beta cancels. Now we have our peak equaling 1 plus e to the minus zeta pi over the square root of 1 minus zeta squared. And that we call y bar sub p. That has a zeta in it. It only has a zeta in it, and it's y bar of p. We also are going to need to find our percent overshoot. We need the final value of y bar. But that's just the limit as s goes to 0 of s, y bar of s. Y bar of s was this omega sub n squared over s squared plus 2 zeta omega sub n s plus omega sub n squared. And I again forgot my s, so let me squeeze that in. That was y bar in square brackets. The s's cancel. I let s go to 0, and what do I end up with? I have omega sub n squared over omega sub n squared, which is 1. Now, what's my percent overshoot? Pictorially, I take this point and this point, and this could be done for y as well as the barred output. In terms of those pieces of information, how do I find my percent overshoot? It's the peak value minus the final value over the final value, isn't it? That's the percent that I overshoot my final value. Well, to make it a percent, I need to scale it by 100%. But in terms of y bar, remember what we just derived this, didn't we? We just derived an expression for y bar. What do I have so many p subscripts? Y bar at t sub p was simply 1 plus e to the minus zeta pi over the square root of 1 minus zeta squared. And what was y final value in the barred notation? 1. So now I have this 1 plus something minus 1. I'm just left with this in the numerator. And what's in the denominator? What was y bar of final value? 1. So now I know what my percent overshoot is. My percent overshoot that's my relationship now between percent overshoot and my damping ratio. What are you going to be calculating from the time domain response? PO, your percent overshoot. Oh, now you have to solve it for zeta. That's doable. Just do some natural logs and some other things. So if we solve this, expression for zeta, because we're trying to find zeta once we've calculated the percent overshoot. Here, let me again refer you to a different location. See note 3 in the demo 1 notes if you want to check your work on solving this formula for zeta. If you do that, you now have zeta is equal to the natural log of percent overshoot over 100 squared all over pi squared plus the natural log squared percent overshoot over 100 all square rooted. That's the second relationship. Meaning, if you now have a percent overshoot of 20%, you plug 20 in for PO. You take the natural log of 20 over 100, square it, save it in memory because you need it again in the denominator. Divide it by the quantity pi squared, which is roughly 10, plus that memoried value. You take that ratio and then you take the square root of that result, and that will give you a zeta. And zeta better be between 0 and 1, because zeta is the cosine of theta. So if you get something that's not between 0 and 1, you've maybe punched something in wrong. That's our second relationship. Now we have exactly where our pole is. We simply need to find alpha. So the third point is to find the gain constant, alpha, and the final value relationship. And we can use the final value theorem to obtain alpha. Meaning, we know what y of s is. That was our unknown transfer function. But we've now found sigma and omega sub d. The only unknown now in that expression is alpha. And we hit it with a step of amplitude A over s. We now say, oh, y final value, and this is the unbarred, this is the original output, this is now the limit as s goes to 0 of s y of s. And what happens there? Well, the s on the far right cancels with the s in front. We plug in s equal to 0 everywhere else, and we end up with, in the first square bracket, alpha sigma squared plus omega sub d squared, all times a. But what is sigma squared plus omega sub d squared? That's just the natural frequency squared. And you can now go to your output response and find, where do you finally settle? That's my final value. I'm going to call that capital A sub 1. That's from your graph. So this is now equal to A1. What's unknown in that expression? You know A, that was how hard you pushed it. You know omega sub n from your first two steps. You know A1, that's where your time response eventually settled. You just solve for alpha. And then you have your transfer function that you needed. Alpha is now equal to A1 natural frequency squared over A. You now have identified your transfer function g of s. That's now alpha over s squared plus 2 zeta omega sub n s plus omega sub n squared. All from your step response, transient response in your lab or experiment. So you've taken experimentally found data in the time domain and identified a second order system that you can now see where its poles are. This is a pure two-pole system. It doesn't have a zero in it. You'll need that on exam number 1. We do have extra office hours tomorrow. Look at the notes or the front of those notes if you need to. Good luck studying. Homework 2 is due today. I'll see you Friday.